Hello everyone, welcome to Tough Math, a channel for math teachers, math coaches, math contestants, and even math enthusiasts. I am Napoleon A. Gacking Jr., a math teacher. The problems featured in this channel come from various national and international mathematics competitions given in the past several years. They appear here either in their original forms or in their repurposed versions. As such, the collection of solved mathematics problems in this channel will be an excellent source of training or review materials, especially for those who intend to compete in some mathematics competitions in the future. So here we are. Our first problem is evaluate this unending product. So m is equal to 1 plus 1/3 times 1 plus 1 3 to the 3 squared, 1 plus 3 to the 4th, and so on. There's no end to these factors. So what is its actual value? That's the question. So first, for convenience, we let x equals 1/3. Then m can be written more conveniently as 1 plus x, 1 plus x squared times 1 plus x to the 4th, and so on, 1 plus x to the 8th. Okay, so there's no end. Now, multiplying the first two factors, we get, okay, so you have 1 plus x times 1 plus x squared. This is easy to multiply because the other term in its factor is 1. So 1 plus x squared plus x cubed. Okay, and then multiplying the first three, factors, we have, okay, so you have 1 plus x squared plus x cubed times 1 plus x to the 4th, which gives us 1 plus x squared, and obviously the highest power of x is x to the 7. And then multiplying the first four factors, so again, the first 4 factors, we obtain so we have 1 plus x plus and so on plus x to the 7, and then the fourth factor is 1 plus x to the 4th, and this gives us 1 plus x squared, and the highest exponent of x is 15. So the pattern suggests that m is actually equal to 1 plus x squared plus x cubed plus x to the 4th and so on plus x to the 15 and so on. Each time the power increases, the power of x increases by 1, and this does not terminate. Okay, which is an infinite geometric series. With common ratio r, which is equal to x, which is less than equal to 1/3, sorry, which is equal to, which is less than 1. This implies that M is convergent, the series is convergent, whose value is m equals 1 over 1 minus x, which is equal to 1 over 1 minus 1/3, which is equal to 1 over 2/3, which is equal to 3/2. So this is the value of m. Okay. Now we go to the second problem of this video. How many odd positive 2-digit, 3-digit, 4-digit, and 5-digit integers are there with distinct non-zero digits, one of which is 6? Okay. So first we remark that the digit 6, okay, the digit 6 cannot be the units digit, because it is even. Okay, so for the 2-digit, this is the simplest case. For the 2-digit case, we have one choice for the 10th digit, because the 10th digit in this case should be, the 6 should be the 10th digit in this case. And we have 5 choices for the units digit. So this is 5, and the digits are actually, since the number is small, I mean there are only a few of them, so we can enumerate them. They are 61, 63, 65, 67, and 69. Okay, so there are only 5, so it's easy to enumerate all of them. However, for the 3-digit, we have more than 5. For the 3-digit, again we have one choice for the digit 6, 5 choices for the units digit, and one choice for the 3rd digit. And since the digit should be distinct, so there you have 7 available numbers to choose from. Okay. However, the 2 numbers, the 6 and the other number or digit, can be switched. So we have to put 2 factorial there. And this gives us 1 times 5 times 7 times 2, which is equal to 70 such numbers. So there are 70 3-digit numbers. One of those digits is 6. Okay, then for the 4th digit, again we have one choice for the 6, 5 choices for the odd unit, 7 choices for the 2 other digits. So we now have 3 digits to permute, so we multiply this by 3 factorial. Okay, because you can switch these other 3 digits, and so we have 1 times 5 times 21 times 6 equals 630. 4-digit numbers one of whose digits is 6 and whose units digit is odd. Then we go to the 5-digit numbers. Okay, again one choice for the 6, 5 choices for the units digit, and then 3 choices for the other 3 digits. And since the tens, the hundreds, and the thousands digit can be permuted to give different numbers, so we have to multiply this number by 4 factorial. Okay, that's the number of ways of permuting the 4 other digits. And so we are left with 1 times 5 times 35 times 24, which gives us 4,000. Which gives us 4,200 such numbers. Therefore, there are 5 plus 70 plus 630 plus 4,200 equals 4,905 such numbers. Let us highlight that. Okay, so there are 4,905 such numbers, no? 5 2-digit numbers, 70 3-digit numbers, 630 4-digit numbers, and 4,200 5-digit numbers. So that's it for this video. I hope you like our problems and the discussion that go with them, and I hope that you are interested in seeing more solved problems in this channel. So if you do, then please subscribe, and see you in the next video. God bless.